Thank you very much. I want to thank to the organization for this excellent conference. I want to talk today about the package SF. SF is a package it's called Simple Features. It's for making maps and making the spatial data analysis, etc. Today I want to try to convince you that we can use the package SF to solve statistical problems not related with maps. And this is a project that we are working in my university. First, I want to talk about some statistical motivation. Imagine that you have some input variables x1 until xp, and these variables produces an output in y, and link through the function called psi. Of course, this function psi could be known or unknown. Generally, it's complex. One question that we can ask is if it's possible to measure the importance of the inputs to the output, and know if you can rank the variables, and also if it's possible to measure the importance. Of course, the answer is yes. We already know that there exist, for example, the Soval indices or pick and freeze Monte Carlo methods, or there are plenty of them. So what we did new, what is the contribution in this work, is exploit the geometric structure of the data to create this rank of importance in the inputs. So the question is how. Okay. First, I want to define two quantities that they are very important for the method. First, I want to define the geometric correlation. Imagine that you can, for example, create a convex hull of the data, and you can create the box containing all the data, for example. And if these two polygons or geometric figures are similar, I will say that the xi and y are geometrically uncorrelated, are noise, in fact. If not, if these two figures are different, I will say that they are geometrically correlated. Okay, with this idea, I can create a quantity called the correlation, geometric correlation of these two variables. Also, we can create a geometric sensitivity index. In fact, imagine that also you have the convex hull of some data points, and we can flip this convex hull over the same axis. And if these two objects are similar, the symmetric difference between them is equal to 0 or near to 0, more or less. So if it happens, xi is geometrically irrelevant to y. Okay. If not, if the other case happens, for example, they are completely different, the symmetric difference will be more or less 2 times the object of the area. So with this idea, I create, I will define this index as Si. This is basically the symmetric difference area for the variable I divided by 2 times the object area for the variable I. Okay, so how do they implement this in the package? The package SF has in fact, two key operations to do that. In fact, affine transformations. This is very easy to do this with SF, and area estimation. This is why I use it. for the to show you, to illustrate how is working in how the procedure is working, I'm going to take this model. This model is a very well known model. It's called the Ishikami model. I'm going to take the second variable of this the model only to show you that the model has an M shape. The clouds have M shape. With this example, I use a paper for Somorodian in 2010 that basically he construct a Vietez-Rips complex using the cliques of the graph or neighborhood graph in the data points. I don't going to enter in all the details because it's a little technical, but basically is not easier, but is direct. So with this kind of construction, I can create triangles overpose over the data points, and afterwards I can join in a whole polygon in SF. So basically, this is what I did: is create a list of all the triangles in the Vietez-Rips, create a union of these Vietez-Rips. For the rest of the procedure, I have to recenter all the points to the origin because we need this for next step. So I have to translate all the polygon to be in the first quadrant of the plane. So I have to subtract the minimum of the coordinates of x and y. For the symmetric deflection, this is a procedure with 3 steps. In fact, we have the reflection. This basically have the original object and create a copy of this object but reflected over the third quadrant. Then we have to shift this object over the same plane in the original polygon, and the last one is create a symmetric difference of these two objects. And of course, with SF, we can make this very easy because with SF, we can create affine transformations only multiplying by a matrix. Very convenient. So in this case, my matrix is 1, 0, 0, minus 1. The shifting is only translate 2 times the mean of the coordinates for the y axis, and the symmetric difference is very direct. Only estimate the polygon by this function. So all this code and all the procedures are in my repository in GitHub. We are trying to finish to send into CRAN. So this is we are almost there. Just to finish, I want to show you some numerical examples. So for the Ishikami model, this is a very, as I told you, this is a very new, new function to sensitivity analysis. This is the result. In fact, if you see the correlations, there are almost 50-70%. The geometric correlation, there are almost 50-70%, and the sensitivity is for the first one is 46%, for the second one is 57%, and for the last one is 11%. So just to compare, the true sensitivity in the sense of the Sobol indices is for the first one is 31, for the second one is 44, and the third one is 0. So in the sense of our method, we can rank the variables in the same way that Sobol indices does. It means it gives the same amount of importance for each variable, only using the reflection of the data. The most curious is, for example, this example, this case. Imagine that you have a donut. A donut is an example with only the data around in a ring around and a hole in the middle. So if I make my package, I run my package with this data, of course the sensitivity will be almost 0 or small. Okay, the true sensitivity in the Sobol index, in the Sobol sense, is 0, of course. But if you know the correlation between the variables is not 0. It means that, for example, for the first variable, the method detects there is a geometric pattern hiding in the model. So maybe this is a great opportunity to search some pattern that is not present in, or is hiding in the analysis that you are making. So what is next? Because this is the package. I'm trying to finish the package. In fact, as a side result, I find that it's possible to create a regression curve using exactly the same object, the complex, using the F package. So this is an example that I did recently. Is just our data. I create like a regression curve using the topological a topological procedure with this method, and I compare with a no parametric regression curve classic in this case. This is very nice because we can create regression curves using topological ideas to solve statistical problems. Of course, optimize the construction of the complex, because this complex is very hard to do with in a computer. In fact, if it depends on the radius of the vitreous ribs. So we have to look for the persistent homology and the barcode, and there is a lot of work to do with this kind of stuff. And of course, the package, I have to send it to Prime. But after there are some books that I have to solve, but we are working on it. So thank you very much.
Thank you. Some questions, comments? Yeah.
Hello, thank you for your talk. So as I understand correctly, you assume that your variables x1 to x3 are independent at the beginning, and you measure basically the sensitivity of the y to the x.
Yeah.
And what happens if you have co-correlates within x variables?
Yeah, in fact, it's a good question, because the next step for this model is to extend it to multiple variables and create, for example, a total sensitivity index. But it depends on the trying to create a simplex and this complex in several variables, and this is a little hard for the moment. add me on the understanding. I don't know, but yes, it's true that if the variables are correlated, this method is not. It doesn't capture all the effect of the model. So the next step is translate all this to several variables. In fact, this is the next thing to do.
Other comments or questions? So I just want to jump on the question because if you think the variable of correlated, so why don't you use your index between the x variable also?
Sorry?
Because you propose a new way of calculating not the correlation, but something. So if you think the x variable are correlated, then you can use your index just to calculate also what you call the correlation.
Yeah. In fact, this is a big issue. In fact, I said the thing is we need to extend this to several variables. And for the moment, there is a lot of work to do with understanding exactly what it means, the correlation between variables in the geometric sense, because because there is a lot of work, theoretical work that we have to do in this sense. My colleagues are more specialized in topology and geometry than me, of course. I'm a statistician, and this is a lot of work to do.
Yeah. And last question: what is the complexity of the method? Because it's huge.
Yeah, it's O n square. Yeah, yeah.